Hello, everyone, and welcome to today's technology webinar on overcoming challenging lighting conditions with eHDR, brought to you by onsemi. I'm Kylie Miller with onsemi, and I'll be your moderator today. In this webinar, we will discuss onsemi's AR0822, an innovative image sensor that produces extraordinarily high-quality 4K video at 60 frames per second. At the end of this webinar, we'll be holding a Q&A session to answer any questions you may have. During the webinar, you can type your questions into the chat box on your right, and we will answer them at the end of the webinar. I will also share the slide deck of the webinar with you during the Q&A session. This webinar will be recorded and posted at onsemi.com. You will be notified via email when the recording is available. Now let's meet today's presenter. Steve Harris works at onsemi as Director of Marketing for the Image Sensors Group. Let's get started with our webinar.
All right, thank you, Kylie. Appreciate the introduction. Hey, everybody. So just a kind of a quick background on me. Steve Harris here, and Director of Marketing for the Industrial and Commercial Sensing Division. I've been in this role actually now for close to a year. Prior to that, actually, I was working on image sensors for automotive for about 8 years. And then even before that, actually, I was working on sensors for industrial and commercial. So kind of coming back full circle here, but have a pretty good, range of ideas of the different applications within image sensing between industrial and automotive. And in all honesty, these are probably two of the areas where HDR is very critical. So I'll start it off by just kind of giving a little bit of a teaser here. So I don't know how many people are familiar with ARRI, but ARRI is a leading cinematography camera in Hollywood. And this is public information, but the ARRI cameras use onsemi for their image sensor. And I want to say, I believe, don't quote me specifically, but maybe the past 8 Academy Awards have been awarded to ARRI. Certainly, you can see here on the right, the best picture went to Everything Everywhere All at Once. That was filmed with an ARRI camera. And even these ARRI cameras have allowed us to even achieve an Emmy. So they actually were gracious enough to help us receive an Emmy for technology. Now, the reason that I mentioned this, and this is kind of in small print here, is that really the details behind the award of the Emmy is talking about one of the techniques actually that we use to achieve HDR. So specifically, the cinematography was actually credited for HDR performance. So I wanted to mention that. And if you have a look at these long list of movies that are out there, impressive movies that are out there. And again, I think this is actually kind of a small list compared to like the total ARRI that uses onsemi. But you watch any one of these films basically, and that HDR and low light and performance is what you're seeing coming from our camera, from our sensor, of course, with the ARRI specialized processing. So I just kind of wanted to put that up front because this right here is what we call a Xyla chart. So the reason it's called the Xyla chart is this looks a little bit like a xylophone. But basically in the cinematography and digital camera world, the way that you measure dynamic range is called f-stops. And how many different f-stops you have really determines the dynamic range of the sensor. This particular sensor that was being used had about 17 f-stops, and that's about 100 dB of dynamic range. So this is just kind of translating, this language of f-stop over into dynamic range, and I believe a stop is about 6 dB. The way this chart works is that there's a light that shines behind it, and then I believe they have kind of a shutter ND filter to block out light, and so you can see it, it doesn't actually quite accurately show how intense it is, but you do get intense light here, and then it goes all the way down even darker. And I think there are charts that even go out to 26, right? But this is a really good, useful tool for measuring dynamic range. Okay, so just before I get started talking about what our eHDR is, embedded HDR, just a really kind of quick primer here on what dynamic range is. So the textbook definition of dynamic range is really the full well capacity of the pixel over the read noise. So that's how we measure it. There's a EMDA 1288 standard, I believe, that uses a similar calculation, but they do the full well over SNR1. So there are different ways of calculating this, but I think, if you look from sensor to sensor across even different companies, generally, I think the way the dynamic range is measured is the full well capacity over the read noise. So that's, kind of the textbook definition. And the need for HDR, the biggest need for HDR is really with scenes, and I'll show some pictures here a little bit later, scenes that have bright lights and dark areas within the same scene. This chart here on the bottom kind of represents what the lux level or the light level is in certain lighting conditions, anywhere from just deep starlight to intense sun. So, generally speaking, when you're outdoor, you're going to run into kind of conditions where you've got some really dark light potentially, and you've got especially bright light. So these markets like security cameras, automotive cameras, industrial cameras, etc., that are outdoors really need this technology. But I'll even add to it. I'm going to do something here for effect. But right now, I'm sitting next to a window, and I just opened the shutter to the window. If I were to move my head over a little bit, you can see the saturation happening in on my head, right? And the reason that that's happening is because this particular PC web camera does not have the dynamic range that's capable of producing a good image. So, hopefully, especially as video collaboration grows, we start to see maybe even HDR going into our PC webcams. But that right there was just even a classic case. I'm not outdoor, of just being indoor and showing you kind of what the effect is of having dark and bright in the same scene. And you just lose a lot of detail. That was kind of illustrative example live there for you. But here's kind of an example for you that is taken in an image, right? So somebody is taking a picture outside from their window. Now, this scene right here, you get a lot of good details in the dark regions. And it's probably because this is a pretty long exposure for the sensor. But what you're missing here completely is any details in the sky. Now, conversely, now maybe we have a shorter exposure. So a shorter exposure capturing less light. Okay, now we're able to make out the detail here in the sky region, but now all of the details here in the dark region have completely disappeared. And so what you'd ideally like is, something like this. This is an HDR image on the bottom right. One of the keys too, especially when you're outdoors, that you can always look for that generally tends to be a good kind of guiding principle on dynamic range is the sky. A lot of sensors have a really difficult time achieving this kind of blue, and you'll see even more crisp blue skies later. But that's always a good indicator kind of to me of sensors that have pretty decent dynamic range, especially when there's sunlight, of course. And here's another example. I think a lot of people have seen the classic funnel. So this is just more of a kind of creative way of showing it. But tunnels are a really good illustration, again, of scenes that have dark and bright, extreme dark and extreme bright within the same scene. And again, the way that a sensor handles that could be that you would have a short exposure where you're getting some of these details in the darker regions, in this case of the cave or the tunnel. But now you're missing the areas in the outside of the tunnel, completely saturated, can't see any detail. Again, conversely here, now we have a shorter exposure. We see all that detail outside the tunnel, but we don't see anything inside the tunnel. So obviously, you could think of automotive in this case, where you're going through a tunnel, a car in front of you has braked and they're just outside of the tunnel, and you have some autonomous driving program, can't see the car, and of course that could be potentially catastrophic, right? So, dynamic range really is very crucial in that type of application. But, another application I could speak to here is maybe, a person walks into a store. There's a lot of light behind a window or whatever glass door that they walk through. And all of a sudden now they're walking into more of a dark environment. You're losing detail in that bright light. You may not identify the person who actually came in and maybe did something. So it's really key. Again, HDR, I think, is really key for a lot of applications. I mentioned automotive, I mentioned security camera, any type of robotics that are outdoors, even indoors where you don't have well-defined lighting, meaning that, you may have windows or really dark areas and windows. So this is where dynamic range is really good. There are, I would say the only application potentially that isn't really as focused as much on dynamic range would be fixed lighting. So there are a lot of applications out there that are more based on active illumination from infrared LEDs or VCSELs. And in those cases, right, the lighting, it's well defined. Maybe in that case, in that circumstance, you don't really need dynamic range. But again, I would argue, even just as I mentioned here, this kind of consumer camera, this PC web camera, right? If I'm going to be doing a lot of video conferencing and I don't have the ability to turn the shutter off on the window, this is going to be my image during the entire presentation. So you can even make the argument, even on some of these consumer applications that are indoors, that is needed. All right, so kind of transitioning here. We want to talk a little bit about the approaches to actually achieve the high dynamic range. So generally speaking, there are kind of three axes for different ways that you can solve the dynamic range issue. The first one would be kind of in the spatial domain, referring to space, size, exact type of photodiode, etc. And I'll show some images later on what I mean by that. But basically, there's architectures that we have what we call a split pixel, a large photodiode and a smaller photodiode, basically all in one. And I'll show you that kind of image to you here soon. There's the ability to do it in the time domain. So this is where maybe you have multiple different exposures over the course of time. Again, I'll show that one. And I won't talk about it too much in this presentation, but there is an approach as well that basically you just, you increase the full well capacity of the pixel. So maybe you just have a really, really big pixel. Maybe you have a small pixel, but you have a lot of capacitance to it, so it's able to store more charge. And so, again, I won't talk about it much here, but what I will say is that I think this is actually a really unique approach to achieving HDR. And it's something that we've used in our products. One of our product families we call Hayabusa, which, you can Google on the web and it will take you to that site on onsemi.com. It uses this kind of approach. This approach is really good because now you have a single exposure or maybe dual exposure where you're achieving a really, really high dynamic range. I think this approach is also potentially really good for LED flicker that you may see again in applications like automotive where brake lights, tail lights, traffic signs, again, are using LEDs. So this is a really unique approach, a good approach. And, certainly a lot of our automotive sensors use this. And potentially a lot of our industrial and commercial sensors of the future may start moving toward this approach as well. But, absent that, if you look at the industrial and commercial kind of industry right now, there are really two popular approaches that are mostly used. The third approach I mentioned right now is kind of emerging in automotive. We'll start seeing it elsewhere, but the need in automotive was critical for LEDs. So the first approach is the one that we're going to focus on, and it correlates very well to the eHDR, embedded HDR technology that we have. So I'll focus a little bit more on this multi-exposure approach. But basically the multi-exposure approach is you have just a single photodiode and you take multiple different exposures sequentially. And in that, you're basically taking effectively different images, at high light, at low light, and maybe at some mid-light level. And then what you do is you merge all those images, you sandwich them together, and you produce a nice high dynamic range image. Now, the other approach that I was talking about is what we call a split diode or split pixel approach. And this is actually a really good X-ray down to the detail of what this actually looks like. Effectively, within the same pixel, what you have is a micro lens that's covering a part of the photodiode. And this would be the larger photodiode. And then you have a smaller photodiode. So in this case, right, you have the ability between this to, expose for longer without saturating, therefore creating, getting the darker parts. And here, you're grabbing the lighter parts and you're combining them together. Now, this is a patent actually that we had dating all the way back to 2009 when we were actually Micron. So I actually come from the Aptina Micron kind of legacy, which is now, of course, broader onsemi. So this is a technology that we've had for quite some time and a patent on for quite some time. Now, I'll talk about it here. There are some reasons why there's drawbacks. Now, the drawback on the multi-exposure approach, really the biggest major drawback on the multi-exposure approach is, again, you're taking images 3 points in time. And so if you have extremely fast-moving objects, you may get motion artifacts as a result of that, because, again, you're taking it at different points in time. There are ways for us to mitigate that, and that's why I put it in yellow. And, I would argue, too, that in order to see those artifacts, you'd really have to have a fast-moving object. And I'll use automotive, classic example. Our automotive sensors have been using this multi-exposure approach, for 10 years, maybe. And, recently, because of LED flicker, we may have moved to a different approach. But even within automotive, the motion artifacts were manageable. It's really, based on angular velocity, of course. And even if you've got a car in front of you changing lanes, may not be fast enough even to produce motion artifacts. Now, certainly if you had a car coming orthogonally to you, that would be an issue. But, that might not be the case for why you may not have a camera on the side of the car that's actually looking for something orthogonal. So again, I think the motion artifacts are something that can be dealt with, but really need to be used just for very fast moving objects. And then going over to the split diode, you can just see right here that you're kind of breaking up. You're not using light efficiently, right? You have gaps in between the large and the smaller photodiode and their micro lenses, right? So it's just, there's some low light loss in quantum efficiency because, you're just not making the best efficient use of space here. And then you may have color artifacts as well, because obviously there's going to be quantum efficiency differences here between the larger photodiode and the smaller photodiode. And then in multi-camera systems, especially ones where you need to stitch images, the consistency with these smaller photodiodes and the calibration, may be different from sensor to sensor. And so could make it really difficult for, 3D mapping type applications or applications with multi-cameras where you need to stitch. So high level, that's part of the reason we really didn't choose this approach to our high dynamic range imaging. And here's just another area right here with the split pixel kind of architecture, is that you do get a lot of crosstalk as well. So you have that smaller photodiode. In this case, we're showing the red here, but it's sitting very, very close to the blue and the green pixels, right? And so now you're actually getting crosstalk between the pixels. And the other element here is that unlike the prior approach that I showed here, where you have exposures and you can change the ratios between these exposures, 16x, 32x. It's very configurable. Here you have really a fixed ratio between the large photodiode and the smaller photodiode. And of course, you can do things with gain to kind of maybe modify that ratio a little bit, but you just don't have the flexibility that you do in a multi-exposure approach. And here's actually a video that actually, one of our competitors put out there. It's actually, again, I mentioned the classic tonal case here, right? Even within their own actual video that they put out there, they actually illustrated one of the issues again with this crosstalk. And you can see that kind of here in this transition region, especially from the light area to the dark area. So again, this is kind of the reason we, as onsemi, have not gone down that route. So what it looks like actually, and I'm showing here a dual exposure, meaning, you have basically two images that you're doing here sequentially. The way it really works, right, is that in a rolling shutter sensor here, you have a sequential readout. So you have a longer T1, and that longer T1 is, of course, trying to capture the dark areas. And then you have another sequentially with it, a T2 or time 2, that's a smaller piece of time, smaller exposure or shorter exposure, meaning that you're able to capture the highlights. And so we have sensors potentially that can go all the way out to 4 exposures. So the more exposures you have, obviously, the more dynamic range you achieve, but also the more complex it is to kind of put those images together. So this is just a pretty easy example of a 2-exposure HDR approach, and the way it actually looks, as we're actually exposing and reading out pixels through to the sensor. And here's just kind of a classic 2-exposure HDR. Where I was mentioning here, again, you have that first long exposure and you have a second short exposure. And then all of a sudden we combine into an image now where you're able to get, details in that dark area and also, details in the light area. So you can see, it's taking this nice blue that I was talking about here from the short exposure, and that's where it is right here. And then you can see in the darker regions that you're taking from the other longer exposure, where you don't have the detail here, right? So it's just a very simplistic way of looking at how multi-exposure HDR works. And by the way, too, for the most part, most of your phones probably use a very similar approach to what I'm mentioning here. Now, what about motion, right? I mentioned motion. Motion, depending on application, may not even be an issue. I would say security surveillance, if it's in a convenience store, or, your doorbell camera, people don't move fast enough generally to really create artifacts that are going to create issues. Again, I would argue in automotive, there are certain circumstances, but, not all the time. But, here's a case where we have a spinning fan. We put it against an orange background so we could kind of see the contrast here. And what you're seeing on the left is a result of motion artifact between the multi-exposures. Now, we have a technology that we've perfected and worked it over, I believe, 10 years on, which we're now calling intelligent linearization. And linearization is basically the ability for us to stitch together these 3 images and get back to an image that has really, really high dynamic range, much like what you see here, right? So in this case, the linearization is the combination, again, of these. Now, we have a process in our linearization where we do motion compensation, and we're able to really mitigate the effects of the motion. So even when we do have motion like this fan, it is something that we can actually correct for. And again, going back to it, right? So now you kind of have the best of both worlds. You have multi-exposure, so you're getting total flexibility in the amount of ratio that you can choose between the exposures. You're achieving up to really high dynamic range. You don't have to worry about the crosstalk. And oh, by the way, that one thing you did have to worry about, which is motion, we've got a methodology for us to correct it. So Again, leading to why this is such a good approach. Now, again, I really think a really unique approach that we do in automotive is this high capacity full well type approach. And, that really, again, is something that maybe a multi-exposure could not solve. And that is LED flicker, where you have LEDs that are on for a period of time, a very short period of time. And, if it misses it in one exposure, or misses it maybe in multi-exposure, if you have 3 and 2 exposures, but you capture it in one, it's going to create some difficulty. So LED flicker, I think, is probably the only single drawback that you may receive from this approach. And even with LED flicker, our intelligent linearization has some ways of mitigating that as well. So even in that case, right, there's ways we can get around it. Just another example right here, we just have something sitting on a vibration plate, and you can even see on this vibration plate, objects obviously moving pretty quickly here, and you can see those artifacts as a result of motion when we don't have the motion compensation or intelligent linearization turned on. And here again, sitting on this vibration plate here, the device is moving, but you're not seeing those artifacts that you were seeing. Again, just speaking to the fact that you can compensate for the motion. And then finally, one of the things that we do, again, as a part of our intelligent linearization, is we smooth out regions of transition. So as I was mentioning, you have multiple different exposures, and it produces a curve that kind of looks like a shark's tooth or, a triangle wave kind of waveform. When you switch from one exposure to the next. And so you do get SNR drops when you take one exposure to the next exposure, right? And sometimes what that will cause is some issues in the transition regions between those exposures. Again, the intelligent linearization that we actually embed onto the sensor is able to compensate for that. Okay, so, I mentioned again the kind of benefits of this multi-exposure approach, especially against some competing type architectures, and I mentioned some of the things that we've perfected in terms of dealing with the significant drawback, which is the motion. And again, motion could happen, may not even be a case in a particular application. So there's also another reason that we want to embed this on the sensor. The intelligent linearization, we know our sensor, we know how to do the linearization of the HDR. All of that is great. But what I'll say is that when you start to have higher resolutions, and rather than doing the HDR and the sensor, we decide, we're going to output those 3 exposures to a processor. And then the processor can do the linearization. Well, if you think about it, you're basically in that case tripling your frame rate, or you're tripling the speed at which that information needs to come across in a 3 exposure case, or in a 2 exposure case, doubling your 4 exposure case, quadrupling it. And now as you start to get the really high resolutions, if we want to produce 120 dB HDR at 4K, 30 frames a second, we're going to have to go up to 12 gigabits per second per camera. And there's not a link there's very few links, I'll say, in the world that can really, at a long distance, handle that. So where cameras are remote to the processor, certainly extremely difficult if the HDR is not done on the sensor. Automotive, great case for that. But, if you start looking at some of these smart warehouses and you start looking at some of these smart buildings, even smart homes, you have many cameras that are located either in close proximity to each other or maybe even far away from each other. And maybe instead of having a processor sitting next to a sensor on every single camera, you may want to do that centralized. And again, if you don't do this HDR linearization on the sensor, it's virtually almost impossible for it to happen on higher resolutions over the cabling that we have. Now, you could also mention here, well, hey, why don't you use compression? Well, in a lot of applications, again, compression, especially the decompression part of it, can produce artifacts. And you don't know necessarily where those artifacts are coming from. So if you're in some sort of application that has AI, machine learning, et cetera, or anything, that's basically what we would call computer vision, not for the human eye, you don't want those artifacts, especially the artifacts that you don't know and are maybe not deterministic. So you really do need the raw bandwidth. And then I'll just even add to that, right? You may have the case where a processor just does not have the horsepower. Maybe it's even sitting next to the sensor, right? But, maybe we have a 20 megapixel camera. Okay, now does first off, does the link work? Are we able to output 20 megapixels at, let's say multiplied 30 frames a second, 3 exposures, 90 frames per second? It's a lot of data. And maybe the processor doesn't even have the capabilities to do it. So this is really what kind of pushes the HDR linearization onto the sensor, this embedded HDR. So multi-camera systems, high resolution systems where the interfaces really haven't stepped up, and processors just purely do not have the resources. And again, what I'm showing here, by the way, with no HDR and HDR enabled on the sensor is literally over a 5x improvement. So again, it's a really strong case to be made that the HDR should be done in the sensor. And maybe even you could, in theory, move from an architecture with a security camera that doesn't have a processor on board because you may have it centralized. So that's kind of what it gives you the ability to do here. Okay, so just kind of shortly here talking about some of the other benefits. I did mention in my verbiage before that it really reduces the need for the processor, the system on chip, to combine these multiple exposures. So, multi-camera systems or really high resolution systems, you don't want to use your SoC's bandwidth to focus on doing multi-exposure HDR because you're going to sacrifice potentially that horsepower in other areas that's needed for the actual ISP or the processor, right? So it just really optimizes the system resource by allowing the processor to focus on other tasks instead of, linearizing the multi-exposure. And I mentioned again back here, but there's no need anymore for kind of a sensor SoC co-location for bandwidth purposes. Because we're now, in this case right here, 5 to 6x kind of improvement on the link. So we can use lower speed cabling and lower speed connectors, et cetera. So cost savings as well by doing that. And that's my third bullet point right here. Cabling in these systems can be quite expensive. The shielded twisted pair, if you crimp the cables, you could break them. So the ability for you to actually use less expensive cabling is actually a system benefit. Same with connectors as well. And then, the other thing that I mentioned here is the motion compensation. This is our sensor. We're taking these multi-exposures. We have the ability through our ISP teams and our design teams to compensate for that motion. And we can do it right at the sensor level. So you really do get some of the best motion compensation you can get because, it's done by the actual sensor vendor itself. So a lot of benefits, again, of this kind of approach of embedded HDR. And honestly, in some cases, almost mandatory. Okay, so now really tying all of this together. What I want to do is talk a little bit about our latest 4K sensor. We're calling the AR0822 here, that we just introduced in press release at Embedded World in March. So a little bit over, I think, about a month ago now. So the 822 uses this embedded HDR approach that I spent some time talking about here. Going back to the xylophone chart slide that I showed earlier, I was showing that RE camera achieved 100 dB of dynamic range. And here it is winning all of these awards, all of these Academy Awards, had gotten us a Emmy for high dynamic range. And again, it's roughly at about 100 dB. Of course, they're working on improving that. We are, etc. But this particular sensor that I'm showing here can achieve up to 120 dB. So all of those beautiful films and pictures that you saw, with basically 100 dB type sensor, now we've cranked it up to 20 dB, even higher. And, I think you could even make a case in automotive, and I actually don't even think you could make a case. I think you need to have maybe even higher than 120 dB. It's good, but some of our automotive sensors will push even higher up into the 150 dB range. So really, really necessary. Now, I would say in scenarios like I'm presenting here, if you get to 120 dB, this is not going to be an issue. What I'm doing right now. It really is mostly going to be when you're staring directly into sunlight. And again, I think you still get pretty good images, but when you come to safety in an automotive world, maybe not acceptable. Now, having said that, the sensor is itself capable of doing that off exposure, what we call line interleave HDR, and that's outputting those exposures to a processor. So it is flexible in that manner. But of course, I think, I'm here to talk about the embedded HDR. I think that's something that obviously we recommend. And again, we have all these years of experience in how to deal with motion during this linearization process, and even potential to kind of mitigate some artifacts as a result of LEDs. The sensor itself is a 4K sensor, can run in linear mode up to 60 frames a second, in HDR mode, the 3 exposures up to 30 frames a second, built on a 2.0 micron pixel, achieves really, really good low light. The sensor itself is what we call a stack sensor. And this is where the array sits on top in a wafer, and then you have a bonded wafer beneath it that is dealing with the logic, the ADCs, and anything digital that we need to do. And so when you have that, you literally, aside from the fact that, you have some packaging tolerances here that you see, you're achieving almost the best in class size that you can get. So from a size perspective, as a 1/1.8 inch sensor here, you're getting the smallest size that you could possibly get by using this stacked architecture. And the other thing, again, I'll mention here is just power. One of the things we've really been focusing on, especially as we go into battery type applications, or there's multiple cameras and we really want to start saving power. An area that we focused on is power. 4K 60, 400 milliwatts. We can go down by 2x, potentially at 30 frames a second. And we have another line of sensors even more optimized for power, maybe with some trade-offs in some other areas. We do have a wide portfolio here. Another key kind of interesting technology, I didn't spend much time on it here to talk about because this is mostly an HDR presentation, is a function that we call wake on motion. But basically the sensor itself has the ability, when it gets certain different light levels from pixel to pixel variation, will basically be able to take itself from a very low power, low resolution mode and basically send an alert to a processor that it's detected motion and turn it on. So it's a really good power saving, unique kind of feature that we've built in here. The applications that I mentioned here, and these are all applications that we do have customers for, and we're seeing, I made the case for the home security camera. I made the case for the professional security camera. Certainly these body cameras now with police and other industries are becoming popular. They're going to be outdoor, right? So they need that kind of dynamic range. Machine vision in cases where you have factories that don't have controlled light. Maybe you want to take a really piece of expensive machinery and move it into another warehouse. You don't know what the light's going to look like in that other warehouse. You want color images, and you need the HDR. And the sensor kind of gives you the cover to do that. Dash cams, I mentioned. This is more of a commercial type application. It even knows automotive. It's sitting on the dash of the car. Now, I will say this, a lot of the OEMs are starting to integrate some of these dash cameras, but dash camera is still a very popular application. A lot of people have insurance rates, for example, that may decrease if they have a dash camera because it's going to record potentially any accident that may happen, right? So there are a lot of good uses here for these dash cameras. especially, insurances and accidents, etc., or even just filming, for your own personal purposes. And surprisingly enough, like I said here, I showed it again earlier, and I won't do it again, but, the notebook camera, video collaboration is becoming huge. And I can't tell you how many times I've sat in a conference room and I've been here just on my web camera, just like I am right now. And I've got a colleague that's sitting across from me, and that colleague's using their web camera. Well, what if we had a web camera here that had high enough resolution and you had a wide enough field of view that person could actually sit next to me, and we both could be talking on the same screen, right? So that's the need for the resolution. But again, the HDR I already pointed to. And, when I'm presenting, I don't know where I'm presenting, what the light conditions are going to look like when I'm on the road, again, having this ability even on the PC web cameras is something I think that hopefully we start seeing. And certainly within video conferencing, I've seen a lot of requests now for HDR, and that means more of kind of a discrete kind of, camera that's just purely focused on doing video conferencing for a room, for example, right? So the applications for this are numerous. As I'd mentioned, HDR critical in every single one of the applications. And especially this kind of integrated embedded approach, really, really important when you have higher resolutions, because the multi-exposure approach, where it's not, the linearization is not done on the sensor, is just really, really difficult to achieve. And of course, we're always going to keep pushing the boundaries, right? We're going to keep pushing resolutions higher. And the rest of the world doesn't necessarily follow at the pace of the sensor. We may be able to put out a sensor every year, every 2 years. The processors may not be able to keep up pace with that, right? They have a longer life cycle. Maybe some of the interface techniques have a longer life cycle, or maybe you're off a generation. And so I think, you can always make the case here that, sure, at some point, we're going to get there with the cabling. We're going to get there with the processors. But that's going to be a generation or two maybe removed if you really want to stay on kind of the tip of the technology curve. So that is what I had here, kind of summarizing. So the beginning case here, HDR really needed for any application with mixed lighting, and especially for harsh lighting conditions where you've got bright sunlight or you've got really dark regions with bright sunlight. There's multiple techniques, as I mentioned. There's the, split pixel approach. There's the multi-exposure approach, and even some of our automotive sensors, the big full well capacity approach, right? There's many different ways to achieve it. Multi-exposure seems to be the most popular within the industry. But again, what you see from a lot of different sensors is that even with the multi-exposure approach, they're outputting those multi-exposures onto a processor who's doing that combination. And again, with what I talked about with the resolutions and the speeds, et cetera, just may not be achievable, multi-camera system, et cetera. And maybe doesn't have the, kind of knowledge that we've acquired for the motion, right? Doing the 10 plus years of motion compensation, may not have that kind of ability or capability on the SoC. And then, so that's where this eHDR comes in and really provides value to you, the customer, or you, the partner, or whoever, by solving these issues with basically doing this HDR linearization on the sensor. And again, I point back to this 822 sensor, great, amazing sensor, low light capabilities. But again, just thinking back to, some of these cameras that are winning Academy Awards and, in these brilliant pictures, this sensor is achieving 120 dB. So it really is quite remarkable. And, we're going to continue to push the limits even higher, of course, in certain generations moving forward. We may, honestly, as LED lighting starts to become more popular, maybe we start adopting, kind of that charge domain type HDR that I talked about within our sensor here, even for industrial. So right now, we're really kind of at the tip of the technology curve for the industrial, for these high resolutions, and we're solving issues at the system levels. But of course, there's always room for improvement. And, onsemi, we continually push the limits of HDR. That's, one of our biggest specialties in terms of sensors is this HDR capability. And we're going to keep pushing higher. But I would say for where we're at right now and the applications that we're serving here, it's at a really, really good level.